the solution to some stochastic PDEs and fail to be unique.
Well, thanks very much, and it's a great pleasure to be here. So, well, and please ask questions. It seems somehow the hall is laid out so it makes it hard to ask them. So I want to, let's see. So before I forget, this is work with Barlow, Mitnick, and Perkins. So let me start with what a lot of people already know, the Yamada-Watanabe theorem. So dx is equal to f of x dt. Let's see, so I just want f of x dB. And f is alpha holder. And we know that alpha greater than or equal to a half implies uniqueness.
But it's 1D, right?
That's right, one-dimensional, exactly. So I was going to mention that still not very much is known about higher dimensions, which is quite surprising. It's been 50 years since we've had this. So this is both strong and unique, strong and weak. And 1/2 is sharp. So the idea is of this talk is to try to get some knowledge about this, like this for stochastic PDE. So we're going to consider the stochastic heat equation. So and this is space-time white noise. And that means we have to do it in one dimension. Okay. So we also want it to be alpha holder, but just to concentrate our mind on a simple example, let me just have it be absolute value of u to the alpha. So and so for this case, with alpha equals 1/2, it's the well-known super process. It's so as people know, this is a limit of branching Brownian motions with the mass of each particle is very small and the time between branching is very short. So it's the limit of critical branching Brownian motions. And it's been very well studied due to the independence of the particles. And we'll use a lot of superprocess techniques for the equation we're studying over there. And so, so a lot of people have studied this, Dinkin, Legal, Perkins, many others, very strong people. And so, of course, they were interested in all aspects of the problem. And what do I mean by alpha equals 1/2? We have this equation. It's a measure-valued process, and in one dimension, the measure has a density which satisfies this equation for alpha equal 1/2. And so maybe I'll make a little box here. Let's see, maybe it's better to do it over here, which describes the status of uniqueness questions. There's strong uniqueness. and weak. And of course, weak, as we've heard, that just means you don't start with the Brownian motion. Your solution includes a Brownian motion, not necessarily the original one. And since I mentioned measure-valued processes, there's also the case whether you're going to consider uniqueness among non-negative solutions or among all solutions. So the weak uniqueness was studied, well, of course, for alpha equals 1, then the function is Lipschitz, and so that's well known. And then alpha equals a half, the weak uniqueness there, let's see, so I should say, so this is also over here, but so for the super process, meaning among non-negative solutions, alpha equals 1/2, that does have weak uniqueness, and we can use a duality technique related to the Laplace transform. Okay. And then actually, Leonid Mitnick filled in this gap. He's very clever with duality techniques, and so he found a dual for the process, which I won't describe. It'll take me a little far afield, but anyway, the answer was yes. Okay, so at least among non-negative solutions, the weak uniqueness is in good shape. And, well, people were interested in the strong uniqueness. And so, so this received quite a bit of attention, and then people essentially gave up. But Ed Perkins has organized a group of us to make a concerted attack on this. And so, following this philosophy, to announce my results at the beginning, it so happens that if alpha is bigger than alpha c, you do have strong uniqueness, strong and weak both. And if alpha is less than alpha c, you don't. Okay, but I'm going to add my twist. I like to keep suspense, so I'm going to wait till the end to announce what alpha c is. So, alpha c equals. So I'll fill in that box at the end.
But you're speaking precisely about the equation on the right.
Well, I'm speaking about this one with, let's see, I erased it, but with an f of u. So in other words, this is going to apply to all alpha holder functions. Yeah. And so, but actually in terms of future work, unfortunately, what we have to say, and you'll see the reason why, it doesn't apply to non-negative solutions. So this is still a question mark. And so we're looking at that, but but there's.
How can you have strong uniqueness for all solutions and not have strong uniqueness for non-negative solutions?
Let's see. Okay, what did I? Oh yeah. Okay. So in other words, yes. So alpha greater than alpha c, yes, and then the question mark goes down there. Thanks very much. Okay. Yeah. As you can see, I participated in the non-uniqueness part. So,
The same alpha c.
Yes, it is. That's right. So, yeah, so I'd like to, so maybe I should make a few remarks about the uniqueness case. And this was done by Ed Perkins and Leonid Mitnick. With input from an earlier paper they did with Anja Sturm. Okay, and this, it uses the technique of Yamada and Watanabe. Okay, that's not the main part of the talk, so that will have to remain a mystery, but it also uses the additional ingredient that, thinking of this case with the u to the alpha, you're saying, where is the non-uniqueness likely to occur? Well, probably where the function is non-Lipschitz. So if you're allowed to make such a statement, the non-uniqueness comes where u is pretty small. Okay, but if u is pretty small, then there's not much influence for the noise. So then, u to the alpha times w dot is small there. So u is smoother than you would expect there. Smoother than usual there, and then you say, okay, it's smoother than usual, so that means, for example, it doesn't shoot away, because smoothness means you have to go up at a slower rate, and so then you say that u stays near 0 more than you would expect, and that makes the noise even smaller, and so forth and so on. Okay. But anyway, this is not my main point, so let me not dwell on that. So okay, well, one of the enjoyable parts of this work is we have a geometric picture that goes along with this. So the strategy of non-uniqueness is we want to have a parameter m, and so we want to add a measure to this equation. So plus eta sub m, depending on t and x. Okay, and then we want to let eta go to 0 weakly as m goes to infinity. And so, and to show in the limit that you get the same equation, so the limiting equation has no eta. And then try to show that with positive probability, you can take a subsequence so something survives, which is non-zero. So we want to take one solution equals 0. And the second solution should have some remnant of what we add, some remnant of this measure here which has survived. The limit of solution with a to sub m, and show that this is that this second u is not identically 0. So that's the idea. And what are we going to add? So I'll make a diagram here. This is x and t. Here's level 2, and here's level 1. And so we want our measure eta to be concentrated in that rectangle. And we make a grid of size 1 over m in both t and x. Okay. And then on every other side, we put a positive mass of 1 over m squared, and on the other sides, we put a negative mass of the same amount. Okay. And so you can see the total mass is 1 if you ignore the signs. Okay, but it's getting closer and closer together, the positive and negative parts, and therefore, if you integrate against the smooth test function, it's going to go to 0, so that means it goes to 0 weakly. So that's what we're going to add. And from now on, let me even concentrate on the case alpha equals a half. Okay, but this is just for the purposes of the talk, so don't believe that this gives away what alpha c is. So we're going to consider alpha equals a half because we want to make use of super process techniques. And actually, I had an earlier paper with Ed Perkins where we had a measure valued, where we had a particle picture for the for these other equations too, with different values of alpha. So there, with the super process, you have branching particles which evolve independently, and if you have power alpha, you have to have systems of particles that influence each other. So in other words, if maybe where there are a lot of particles, the branching in depth speeds up or slows down depending on what alpha is. Okay. Well, alpha equals a half. So if there were only positive particles, we'd have the super process. Well, what about negative ones? Well, I guess they could do their own super process. But how do they interact? And after a little bit of thought, you decide you would get a solution to this equation if you have the particles annihilate when they meet. So plus minus particles annihilate when they meet. Now I should emphasize too, we have a technique called the historical process. So what this does is it allows us to go to the limit. And so, in other words, you may think when I'm speaking of particles, I'm talking about the approximating picture. But for the super process and the historical process, which is a technique having to do with it, you can actually go to the limit and still talk about particles. So the measure would represent the amount of particles you have. What the historical process is, it's a measure on the paths. It's a measure on paths. So h sub t is a measure on paths up to time t. And what these paths represent is the history of the particles which are alive at time t. And so this was developed by Dinkin and Perkins. It's a beautiful piece of mathematics that allows you to say things actually in the limit. So we use this quite a bit. So our earlier work also developed a historical process for that equation there with an alpha which is not equal to a half. Okay. So what we want to look at first, since we know if something survives, what stops it from surviving is going to be the death, the annihilation of the particles. So we want to show that annihilation doesn't kill everything.
So what, one type of particle wipes out the other? And then
Yeah, I mean, what you might think, these particles are all, so you have to imagine that, every other person in this room is an alien made of antimatter. So probably, immediately everybody would blow themselves up and there would be no survivors. But we want to show in this situation that there are. Oh, and I should make a plug too that Tom has his own version of this, the look-down process, and so probably later he'll tell me how to redo the argument using the look-down process. So. So we'll do this in two stages. So first of all, let's just consider the positive mass. Okay, so I'm going to reproduce this picture here, but only putting the positive particles. This is level 1 and 2. Okay, and so the total amount of positive mass is a half. So the probability of survival up to time 2 is positive, no matter how finely we subdivide this mass. The probability of survival time 2 is positive uniformly in M. Oh, and I should probably also say that the equation, without the negative mass, the equation for the positive mass is just the familiar Feller diffusion, which I think has already been written down here. If the total mass is Zt, then dc is square root of c dB. Of course, there's immigration, so I'm not including that. Just if the mass started just at a single time, then that would be how it evolves. Okay. But it's known that these critical branching processes, if you start with a very small amount of mass, it dies out quickly. So most of these, and these are very small, they just have mass 1 over m squared. So in fact, most of these will die out almost immediately. Before time 2. And in fact, only a finite number will survive. If they started all at the same time, the number would be Poisson. And it would also be Poisson irrespective of m. So no matter how many subdivisions you have, the existing mass here will only have a finite number of ancestors, maybe this one and this one. Okay. And the rest will die out on their own, even without the killing from the negative mass. So what we want to do is concentrate on one of these and condition it being the ancestor of all the mass at time 2. So condition on one cluster being the ancestor of the mass alive at time 2. So there's a positive probability that there's only one ancestor. And of course, it could all die out by time 2, but there is a positive probability of this. There's also a positive probability of more than one ancestor, but let's just concentrate on this. So let me see. So here it is. And then here would be time 2. And so now we need more precise information about how this grows. So the total conditioned mass, now we're conditioning, so the equation for the total mass is not going to be this anymore. And after some computation, you find that the total conditioned mass evolves in this way, square root of z dB plus a constant dt, approximately, if it were, so it's pretty close to this. I'm not going to worry about how it's different. So this is a good exercise. Also, if you want to take a break from the talk and think about this. So then, also, what about the spatial motion? One can decide also that it spreads like a parabola. Okay, now I should remark that, okay, it's the heat equation, and we know the heat equation doesn't have compact supports, so what am I saying over here? Well, remember that critical branching processes die out almost immediately if you start with small mass. But, if the mass starts here, what's outside the parabola, if you fatten it a little bit, is going to be a very small amount of mass. So then you can sort of see that perhaps it would be supported inside a parabola. So we're going to assume that. So this is a parabola. Okay. And let's even somehow forget about this. Let's say it, so roughly speaking, Zt is about a constant times t, something like that. So this is the conditioned mass, conditioned to be the ancestor. Okay. Now, so we have the behavior of the ancestral mass. Now what happens with the killing? So let me start to put in some blue particles here. Let's look up to time. This is, who knows what this time is? Let's say it's time s, and here's time s plus t. So then there's some blue mass. So, well, actually, there are two parts. There's, okay, the blue mass that's in here could certainly kill out the mass that I've just shaded. Okay, but there could also be blue particles from down below. So they could come up and do the killing. I'll call that scenario 2. But let's consider number 1 first. So let's consider killing by blue particles of type 1. Okay. Well, these blue particles also spread in terms of parabolas. So, you know, if you look up at a parabola starting here, you know, so what blue particles have parabolas which intersect the shaded parabola before this time s plus t? So I claim it's a region which has mass comparable to this rectangle that I'm drawing. So in other words, roughly speaking, the blue particles which could of type 1, which could do the killing of this red particle, would be located inside the rectangle, or maybe a little bit beyond. So, so we need only consider particles in the shaded rectangle. Okay, and we'll see how much mass there is for those particles. Okay. Well, this is a parabola. It has, we're looking at it at height t, and therefore the width is going to be square root of t. So the mass of these particles that can kill would be t to the 3/2. And so we have to compare that to the mass of the red particle, which we have here. So the mass originating from the red particle. And that's t, and we're dealing with small times. So t is much bigger than t to the 3/2, so the killing doesn't win out. So that's the rough argument. So that's 1/2 of it. So that's how we deal with the blue particles of type 1. So maybe, actually, it looks like there's going to be plenty of time, so maybe I should see if there's any questions at this point.
Why is t small?
Well, I took levels 1 and 2, but we only have to take, it doesn't really matter what level we take, so I could take small levels instead of 1 and 2. So in other words, the red mass doesn't have to actually go up to, survive till time 2. It could just survive a short time, as long as that short amount of time doesn't depend on m. Okay. So that deals with particles of type 1. Now we have to consider particles of type 2. So, so what they could do is, come up here from the past and then go into this region and kill and do their killing of the red particles. Okay, but so this is a little worrisome because down here you actually have quite a few of these blue particles, and so it seems that there's too much mass to eliminate somehow. But actually you can draw rectangles below as well. So you can kind of draw a picture like this. So I'm thinking of a sequence of rectangles up here, and maybe the only blue particles I want to consider for the killing at this stage are the ones I've shaded over here. And in fact, let me even, since it's easier to explain, let me just ignore the sides over here. And let's just, I'll call this particles of type 3. So I just want to consider those, and here's what we get. So this is of size t, and so here, these divisions will be of size t over 2 each. And the width of this rectangle, well, again, it's comparable to square root of t. So the mass of the blue particles in region 3 is, again, about t to the 3/2. And so their total mass, I mean, they're killed by the red particles, but if we ignore that, their total mass would be a super process. And so the question is, could they live long enough to come up here and kill the red particles? So the question is, with a critical Feller branching diffusion, how long do you live typically? Because we know that a critical branching process dies out. So for a Feller diffusion, dz is square root of z dB, and z at time 0 is little z0. So remember, the blue particles are not conditioned. So they just satisfy the usual Feller equation, and it's known that the time to death is about the initial mass. Which in this case is about t to the 3/2. But the time that we have available before they do their killing is about t over 2. So time available is t over 2. And once again, there's much more time available for them to die than we need. So in other words, these particles here, with high probability, they'll all die before they get up here and are able to kill the red ones. Then you have to do a similar argument for these shaded regions to the side. So you have to measure the distance, the lateral distance from those to the parabola up there. And so that turns out to be similar. So in other words, so the conclusion is that neither regions 1 nor 2 can lead to probability 1 killing of the red mass. So this is how we prove that, modulo many details, this is how we prove that the probability of survival is positive, and that positive number doesn't depend on m. So we get something, and that was the goal here. So number 2. So we do get this solution which isn't identically 0. And let's see. So let's see. Unfortunately, all this may not help you to guess what alpha c is. I'll do 2 of them. So I wonder if anyone has a guess. So it's less than 1. No, it isn't a half. So it's 2/3. We originally thought it was 2/3. That was our first argument, and I like that because then I could say, okay, we have this all these numbers t to the 3/2 there in both cases, so that would explain it. But then we were able to refine the argument and get non-uniqueness all the way up to alpha equals 3/4. So I haven't come up with a good intuitive reason for that. It just comes out of the calculations. And so that's and that was lucky because that's what Ed Perkins and Leonid Mitnick in their proof of uniqueness, they got it for alpha greater than 3/4. So we have a complete result, and people have asked me what happens exactly at 3/4. We don't know that. So there are various questions. What about colored noise and so forth? But so this was enough work for the moment. So that's where we stand.
So you have a non-zero solution for the case alpha being 1/2, right?
That's right. Yes. So.
And why is it non-negative? It's not supposed to be non-negative, right?
Yeah. The trouble is, see, you have these plus and minus masses, and they both have to be there. So I showed there was a positive probability of the positive mass surviving, but you can't rule out the possibility some negative mass also survives. And so it seems essential because you have to the total mass of what we added is 1, and it only weakly converges to 0 because the pluses and minuses cancel out. So this strategy is not going to give a counterexample for non-negative solutions. So remember we have for non-negative solutions we have weak uniqueness. And so what you're going to have in that case, so as I was saying, the problem seems to be at the boundary of the support, but you have weak uniqueness, and so it looks like, near the boundary, if you want to construct a counterexample, you're going to have to send some of the mass down on part of the probability space, and up on another part of the probability space. In other words, you have to produce something with a solution, a second solution with the same probability law, and the discrepancy has to occur near the boundary of the support. So this is very delicate. Actually, there are some estimates for the Hausdorff dimension of the boundary of the support, but your first calculations indicate that they're not, that the boundary of the support is not big enough to do what you want, and so it means you have to be more clever than this first attempt. So it's still open, but we don't have any idea how one would show strong uniqueness if that happens to be the case for parameter 1/2, for alpha equals 1/2. So it seems like that people swing one way or the other. You try for a while to prove uniqueness, and then you say, oh well, it must be non-unique, and then you try the other way, and you change your mind again, and so so neither one argument has succeeded.
In the case of diffusions, in fact, one has also some conditions which are a bit more precise by involving some function h, such that 1 over h squared is not around 0. So do you expect to get something of this type around alpha c?
This is a criterion for what happening?
For pathwise uniqueness.
Right, yes. So, yeah, that might be a good idea. So the question is how to get a more precise result, saying, for example, what happens exactly at 3/4. So, but there are a lot of steps to this argument, and, Yamada Watanabe is you write down a function, and then, you apply Ito's lemma and so on. So this is more involved, the construction of the counterexample here, and then as I was saying, with the proof of uniqueness, which I also said, I didn't participate in that, but it was one of these long productions that Ed Perkins tends to be involved with, and as I mentioned, you have to iterate. You have to say, well, assuming just the usual continuity modulus of continuity on U, then you get some estimate of how fast this increases at the boundary, and then you say, well, based on that, the noise is small where U is small, and so it's actually a little smoother than that, and so U is increasing more slowly, and so it's still closer to 0 than you think, and so you can, again, the noise plays less of a role, and you can make it even smoother near the boundary, and so I think they may have sort of an iterative approach with an infinite number of steps like that, and then.
If you change the noise, so from now, when you have Kalman multispace L2 to somehow Sobolev space H alpha 2, do you have any idea what could happen?
Say that again. If you change the noise, what?
No, you have the Kalman multispace noise, which is L2 in your case.
Yes.
So you can change it to some fractions, Sobolev space H alpha 2, with alpha positive and negative.
Yeah, that certainly would be something to consider next. So, as I was saying,
do you have any ideas or any thoughts?
Yeah, well, only that this previous paper with Perkins, Mitnick, and Sturm has a criterion for, based on the covariance function, what the critical power is, and I don't happen to remember the relationship, but that would be a first guess. But I mean, if you have colored noise also, so then the question is, what do you do with the super process? And you know, actually that hasn't been considered. So we have a super process for different powers of alpha here, but we don't have it for colored noise. And you know, probably you could get some sort of something like that, and maybe that's what we should do next.
Isn't it the case that their colored noise paper doesn't quite go all the way down to the white noise case?
Yeah, it doesn't. So after that, then Leonid and Ed, you know, improved it, as I said, and you know, so it may be that the earlier paper was suboptimal. I don't know, or maybe it was optimal for the colored noise case.
So there's no more question. Let's thank Carl again.